Dimensional Jacobian matrix. Introduction. The Jacobian plays an important role in the analysis, design, and control of robotic systems. The Jacobian matrix can be expressed by two columns: J is equals to J1 comma J2, and J1 and J2 belongs to R to the power of 2 cross 1. Then the velocity relation is given as follows: VE is equals to J1 theta 1 plus J2 theta 2. The first term The first term on the right-hand side accounts for the end effector velocity induced by the first joint only, while the second term represents the velocity resulting from the second joint motion only. The resultant end effector velocity is given by the vectorial sum of the two. Each vector of the Jacobian matrix represents the end effector velocity generated by the corresponding joint moving at the end unit velocity when all the other joints are immobilized. Figure illustrates the column vector J1 and J2 of two DOF robot arms in the two-dimensional space, and vector J2 given by the second column of the Jacobian matrix provide points in the direction perpendicular to the link 2. Note, however, the vector J1 is not perpendicular to link 1 but is perpendicular to line OE, the line from joint 1 and to the endpoint E. J1 represents the endpoint velocity induced by joint 1 when joint 2 is immobilized. In other words, like link 1 and 2 are rigidly connected, becoming a single rigid body of link length OE, and J1 is the tip velocity of link OE. In general, each column vector of the Jacobian represents the end effector velocity and angular velocity generated by the individual joint velocity, while all other joints are immobilized. Let P be the end effector velocity and angular velocity, or the end effector velocity for short, and Ji be the ith column of the Jacobian. The end effector velocity is given by a linear combination of the Jacobian column vector weighed by individual joint velocity. P is equals to J1 Q1 so on to Jn Qn, where n is the number of active joints. The geometrical interpretation of the column vector is that J1 is the end effector velocity and angular velocity when all the joints other than joint 1 in a is joint 1 are immobilized, or only the ith joint is moving at a unit velocity. Remember that the end effector velocity is given by the linear combination of the Jacobian column vectors J1 and J2. Therefore, the resultant end effector velocity varies depending on the direction and magnitude of the Jacobian column vector J1 and J2 spanning the two-dimensional space. If the two vectors point in different directions, the whole two-dimensional space is covered with the linear combination of the two vectors, that is, the end effector can be moved in an arbitrary direction with the arbitrary velocity. On the other hand, the Jacobian column vector are aligned. The end effector cannot be moved in an arbitrary direction. This may happen for particular hand postures where the two links are fully contracted or extended. These arm configurations are referred to as singular configuration. Accordingly, the Jacobian matrix helps singular at these positions. Using the determinant of a matrix, the condition is expressed as that J is equals to 0. J is equals to a matrix minus L1 sin theta minus L2 sin theta L1 cos theta 1 L2 cos theta 2. The vectors j1 and j2 joints are same directions if theta 1 is equals theta 2 and if theta 2 is equals 180 plus theta 1 minus L2 sine of a 180 plus theta 1 is equals to L2 sine theta 1. L2 cos of 180 plus theta 1 is equals to minus L2 cos theta. Transformations. Description of a position. Once a coordinate system is established, we can locate any point in the universe with 3 cross 1 position vector. Because we will often define many coordinate systems in addition to the universe coordinate system, vectors must be tagged with information identifying which coordinate system they are defined within. The position vectors are written with a leading superscript indicating the coordinate system to which they are referenced. For example, AP. With this means that the component of AP have numerical values which indicate distances along the axis A. Each of these distances along an axis can be thought of as the result of projecting the vector onto the corresponding axis. Description of orientation. Often it is necessary not only to represent a point in space, but also to describe the orientation of a body in space. For example, if vector AP locates a point direction directly between the fingertips of the manipulated hand, the complete location of the hand is not specified until its orientation is also given. Assuming that the manipulator has a sufficient number of joints, the hand could be oriented arbitrarily while keeping the fingertips at the same position in space. In order to describe the orientation of a body, we will attach a coordinate system to the body and then give a description of this coordinate system relative to the reference system. In the figure given below, the coordinate system B has been attached to the body in a known way. A description of B relative to B A has now suffices to give the orientation of the body. Thus the position of points are described with vectors and orientations of bodies are described with an attached coordinate system. One want to describe the body attached coordinate system B is to write the unit vectors of its three principal axes in terms of coordinate system. Description of a frame. The information needed to completely specify the whereabouts of the manipulator hand is a position and orientation. The point on the body whose position we describe could be chosen arbitrarily. However, for convenience, the point whose position we will describe is chosen as the origin of the body attached frame. The situation of a position and orientation pairs arises so often in robotics that we define an entity called frame, which is a set of four vectors given position and orientation information. Mapping involving general frames. Very often we know the description of a vector with respect to some frames B and we would like to know the description with respect to another frame. Here the origin of frame B is not coincident with that the frame of A but has a general vector offset. The vector that locates B's origin is called AP borg. Also, B is rotated with respect to A as described as ARB. With given BP, we wish the compute AP had as in the figure. The above equation describes a general transformation mapping of a vector. The form of the above equation is not appealing as a conceptual form. That is, we would like to continue of a mapping from one frame to another as an operator in matrix form. This aids in writing compact equations as well as being conceptually clear. In order to write the mapping equations in the compact form, we define 4 cross 4 matrix operator and use 4 cross 1 position sevators so the above equation has a structure. Compound transformations. In the figure, we have CP and wish to find AP. Frame C is known relatively to form frame B and frame B is known relatively to frame A. We can transform CP into BP as BP is equals to BTC CP and then transform BP into AP as AP is equals to ATB BP, combining these equations. Robot kinematics matrices. For given value of the joint variables, it is important to be able to specify the locations of the link with respect to each other. This is accomplished by using the manipulator's kinematic equations. We use associative with each link I a coordinate frame x1, y1, z1 fixed to the link. A standard and consistent paradigm for so doing it is the Denavit Hartingberg representation. The frame attached to link 0, the base of the manipulator, is called the base frame or inertial frame. The relation between the coordinate frame I1 and coordinate frame I is given by the transformation matrix. The commonly used convention of the first selecting frames of reference in robotic applications is the Denavit-Hartingberg or DH conversion. In this convention, each homogeneous transformation AI is represented as a product of four basic transformations. Example, three-link cylindrical manipulator.